We're going to shift gears here now. This unit is called circular motion and gravitation. We've covered the basics of circular motion already. Now we're going to start talking about gravitation. Now, how are those two related? Well, when we talk about the Earth going around the sun, it moves in more or less a circular path, which is caused by gravity. So you can see how we're going to put the two together now. Gravity, which attracts the Earth to the sun, and circular motion, which is the actual path that the Earth goes around the sun. We're going to talk today about a little bit of history, some development of heavenly motion notions, the ideas that we currently have of heavenly motion. But we're going to go way back first and talk about Aristotle and a guy named Ptolemy, like 2,500 years. Aristotle was 4th century BC, before the birth of Christ. Ptolemy was about 140 AD, about 140 years after the birth of Christ. Both of these guys suggested what we call the geocentric theory. That is, that the Earth is the center of the universe. Geo means Earth, centric means centered, the Earth-centered theory of the universe. In other words, the sun, all the stars, all the planets, everything that you look up in the sky at nighttime and see, everything revolves around the Earth. Now, we know this is wrong. Right? We know today this to be dead wrong. The Earth is not the center of the universe. The Earth revolves around something else as opposed to something else revolving around the Earth. But if you stop and take a step back for a second, how do we know that? How do we know? How do you know that the Earth is not the center of the universe? Not because you look up in the sky in the morning and see and say, oh, look, the Earth is moving. The Earth is moving around the sun. When you look up in the sky in the morning and see the sun rise in the east, and then later on in the day you see it in the south, and then later on in the day you see it in the west, if somebody didn't tell you otherwise, you'd probably think the sun was revolving around the Earth, right? I would. Okay? I don't know if I'm smart enough to know that the Earth revolves around the sun unless somebody tells me that. You know that the Earth isn't the center of the universe because somebody has told you that the Earth isn't the center of the universe. And we think 2,000 years ago, how could these guys be so wrong? Well, because most of us today would still be wrong if somebody didn't tell us the difference. So it's not so far-fetched after all. It is wrong, but it's not such a far-fetched notion after all. All right. We're going to zoom forward here, 1,500, 2,000 years, to about 1543. Copernicus, you've heard his name before, right? Copernicus. He suggested what we call the heliocentric theory, which says the sun is the center of everything. Helio means sun. Centric, centered. The sun is the center. All the planets, including the Earth, Mars, Jupiter, all the other planets revolve around the sun. That idea was pretty controversial at the time. It doesn't make any sense to most of us who look up in the sky and say the Earth is the center because everything appears to revolve around it. 1543, we didn't know any different. It's one guy telling us that, no, wait, the sun is the middle. The sun is in the center. Nobody believes it. It's pretty controversial. Let's fast forward a few more years here now. Still same century, latter part of the 16th century, to a guy named Tycho Brahe. Tycho Brahe made some observations. He didn't really do anything with those observations. He just made some observations with an assistant of his named Johann Kepler. He's going to be an important guy in just a moment here. Made observations of the stars and the planets, measured angles and times and distances and so on and so on and so on. Didn't do anything with it, but laid the foundation for some things that Johann Kepler did later on after Tycho Brahe died. After Tycho Brahe makes his rather odd exit from the world, his assistant, Johann Kepler, takes the data that the two of them collected, these observations that the two of these guys made, and formulates 3 laws that describe the motion of the planets. So he's late 1500s as well, right? Because he's with Tycho Brahe. Using that data, he formulates these 3 laws that describe how they move, how the planets move. Okay, what's the path of the planets? What's the shape of the path? And so on. We're going to talk about those 3 laws in a little bit more detail in just one moment. Here's the first of his 3 laws. It's called the law of the elliptical orbits. Now, the diagram that you see right now isn't going to make any sense to you, right? There are not 2 suns. We don't have 2 suns in our solar system. We have 1. But, bear with me for a second. The law of the elliptical orbit says the Earth, or any other planet for that matter in our solar system, orbits around in an elliptical path, right? Not a circle, an ellipse. An ellipse is like a stretched out circle. Now, understand that the diagram that I have of the ellipse drawn up here on the board is an exaggerated ellipse. It's not stretched out nearly that much. It's much closer to a circle than it appears in this diagram. I just want to show you that it's not a circle, okay, that it is an ellipse. Every ellipse has what we call 2 focal points. There's a focal point right here and a focal point right here. The sun will be at one of those focal points. Now, we're not saying that the sun switches positions. It doesn't. We're not saying that the sun is at both points. It isn't. The sun is either here or the sun is here. Now, the sun doesn't just decide where to go based on the orbit of the Earth as well, based on the ellipse of the Earth. The sun is fixed. The sun is where it is. It's the orbit of the Earth that decides where to go based on the position of the sun. So if the sun is here, then the Earth either goes around it like this, like you see in the diagram, or it would go around it like this. The sun is in a certain position. That sun has to be at one of the focal points of the ellipse that the Earth takes. Now, if the sun happens to be at the other focal point, right here, well, then the Earth can orbit around it like you see it right here, or the Earth could orbit around the sun like this, with the sun at the right-hand focal point. Bottom line is, the sun is where it is. The ellipse that the Earth takes around the sun forms such that the sun will be at one of the focal points of that path. So, how do we put the law of the elliptical orbits in words? I could say that the Earth revolves, or the Earth, or all planets revolve around the sun in an ellipse with the sun at one of the focal points. Planets revolve around the sun in an ellipse with the sun at one of the 2 focal points. Second law, this diagram's even wackier here. Second diagram, or the second law, is called the law of equal areas. Bear with me on this. Clearly you can see an elliptical path of the Earth going around the sun in the middle here. Here, let's color the sun in yellow. So we're choosing the position that the sun has to be, right? We know it's going to be at one of the focal points of the ellipse. We're making it the left-hand focal point of the ellipse in this particular case. It doesn't really matter which one it's in. We're going to say at one moment in time, the Earth, or whatever planet that we're talking about, is right here. At another moment in time, let's say T1 later, maybe T1 represents 6 days, maybe it represents 3 months, maybe it represents 6 months, 4 months, 17 days, whatever. Okay, a certain amount of time later, E, the Earth, or whatever planet, is in a different position. Now, if we say that we have a line joining an imaginary line joining the Earth to the sun, then that line, as it goes around here, as the Earth rotates around or revolves around the sun, that line will sweep out a certain area that we're going to call A1. So this area in here is going to be called A1. So in a certain amount of time that we call T1, a line joining the Earth to the sun sweeps out a certain amount of area. Now, honestly, I have no idea how we would calculate that area. That's a crazy mathematical shape. right? It's one portion of an ellipse. Okay? Somebody that's smarter than me can find the area of that section of the ellipse that was swept out. Bottom line is it can be done. Okay, there is an area there. Now let's fast forward maybe 6 months. The Earth is over here. Well, a certain amount of time later, the Earth is right here. The time interval in the first section over here on the left-hand side was T1. The time interval over here is T2. Now, if T1 equals T2, in other words, the time interval in between the Earth's position here and here, if T1 equals the time interval between the Earth's position here and here, if T1 equals T2, in other words, if the amount of time elapsed between here and here is the same as the amount of time elapsed between here and here, then if T1 equals T2, then A1 will equal A2. The area swept out over here will equal the area swept over here. That doesn't make any sense, right? This is a longer section of a triangle here, right, than we have on the left-hand side, but it's skinnier as well. The total area ends up being the same if the time interval is the same. We could state this in words, although I think the diagram makes more sense than the words. During equal time intervals, a line joining a planet to the sun sweeps out equal areas. So during equal time intervals, okay, T1, T2, a line joining the Earth to the sun will sweep out equal areas, A1 and A2. So if those two times are the same, then those two areas will be the same. I don't know if any of you were thinking the same thing that I would have been thinking the first time I saw this. So what? Who cares? Well, this has some pretty big implications, actually, and this is pretty important. As much as right now it might not seem it, it is. Why? Well, look, if the Earth travels this distance during a certain time, and then later on, 6 months later, it travels this distance during the same amount of time, and it has to, right? The distance has got to be different here, because in order to have a stretched out, I want to call it a triangle. It's not really a triangle, but in order to have a stretched out triangle, that side can't be as long. It can't be. It travels less distance over here in the same amount of time as it travels more distance over here. Then the implication that has is that the Earth changes speed. The Earth's going around the sun, and we think of it as traveling at a constant speed, but it isn't. When the Earth is closer to the sun, it's traveling slower or faster. When it's closer to the sun, it's traveling faster. It's going to cover more distance in the same amount of time. Now, I said before when I drew the ellipse, it's an exaggerated ellipse. Right? The ellipse isn't nearly stretched out as much as I've got it drawn here. So that means the difference in speed is quite exaggerated as well. But there is a difference. The Earth gets closer to the sun, it speeds up. It's further away from the sun, it slows down. Right? It goes something like this. Kind of slingshots it out, right? It's going faster as it gets closer, and then slingshots it out. And the third law, the law that we call the law of periods. The law of periods says, bear with me before you write anything down here, okay? The law of periods says the square of the period of revolution of a planet around the sun is proportional to the cube of the radius of revolution of a planet going around the sun. Now, I know that doesn't make any sense with the way that I've said that. So let me write it down in a mathematical formula type way. We're going to say t squared, and that's the average period of revolution of a planet going around the sun, over r cubed, which is, we know that r changes, right? Okay, we know that the ellipse has the sun at one of the focal points, and r is therefore going to change. But on average, what r is, t squared over r cubed is going to be equal to a constant that we're going to call k, Kepler's constant. Now, here's the thing. Kepler's constant is a constant, but it's not what we call a universal constant. That means that it's a constant for a particular thing being orbited around. We call it a central body. The sun is a central body. The Earth orbits around the sun. Mars orbits around the sun. The Earth can be a central body. The moon orbits around the Earth. The space station orbits around the Earth. Okay, Kepler's constant is the same for a particular central body, but different for different central bodies. So for instance, Kepler's constant for, let's say, for the sun may be equal to the period squared of the Earth's revolution around the sun divided by the average radius of the Earth's revolution around the sun. Kepler's constant for the sun could also be equal to t squared over r cubed for Mars. Kepler's constant for the sun could also be equal to t squared over r cubed for Jupiter or any other planet. So this is a big deal too, because what we can do here is use data for one planet, let's say the Earth, to find Kepler's constant, and then use Kepler's constant to find data for another planet. Because that value, that ratio of t squared to r cubed is going to be the same for any planet revolving around the sun. Now, having said that, we could say Kepler's constant for the Earth might be equal to t squared over r cubed for the moon. The period of the moon's orbit around the Earth, the radius of the moon's orbit around the Earth. We could say Kepler's constant for the Earth might be equal to t squared over r cubed for a space station. But what's important to note here is that Kepler's constant for the sun is not the same as Kepler's constant for the Earth. Okay, the Earth is the central body for the moon and the space station. The sun is the central body for all the planets. And Kepler's constant is the same always for the sun, no matter which data, which planet you're using. Kepler's constant for the Earth is the same no matter which thing you're using. But these two Kepler's constants, Kepler's constant for the sun is not equal to Kepler's constant for the Earth. That make a little bit of sense? So we're using data from one orbiting object to find data for another orbiting object. Maybe we've got data for this space station going around the Earth. We can use it to find data for the moon orbiting around the Earth. Or maybe we've got data for the Earth orbiting around the sun. We can use that to find data for Jupiter orbiting around the sun.